Hello. In the last lecture, we had a look at prefix adders, which was a faster and more practical implementation of an adder. So now we move on. The first topic we'll see, first component that we'll see today is a subtractor. Basically, how a subtractor is implemented. Now, if you remember basic binary arithmetic, you will remember that this a minus b is basically a plus 2's complement of b, right? And this 2's complement of b can again be split into 1's complement of b plus 1. What is 1's complement of b? That is basically inverting or negating each bit of b. That is what we are doing here. So this is a block representation of a subtractor a minus b, n bit number, the subtraction symbol is there, and here you will get an n bit answer. So this is actually implemented using an adder, and a is taken as it is, b is inverted to get the 1's complement, and to add this extra one to find the 2's complement of b, we give a cin equal to 1. So this is basically a plus 1's complement of b plus 1. So that is how we implement a subtractor. Now moving on to the next topic, comparators. So in digital logic, we can basically, there are two type of comparators, namely equality comparator and magnitude comparator. So equality comparator is simple. The idea is that we want to know if two numbers are equal or not. The relative value of the two numbers are irrelevant. We just want to know if they are equal or not. So, so how do we know if two numbers are equal? One method which is more efficient in digital electronic paradigm is comparing them bit by bit. Right? If two numbers are equal, each digit of corresponding position will be having same value. So that is the same logic we are implementing here. Here we compare the first bit LSB, if they should be equal, and the next one should be equal, and the next one should be equal, so on and so forth, and every element should be equal, right? So in digital electronics, which gate is used for comparing or checking if two elements are same or not? We can use XOR or XNOR, but here we want a result in 1, right? That is, if we want if A and B are both the same, we want the output of the gate as 1. If we use XOR, that is not possible, but that is why we are using XNOR, right? So first we compare the first bits A0, B0, and the next two corresponding bits A1, B1, like that, so on and so forth till the MSB. So, and we AND all of them together, AND gate. So unless and until all of these cases give a 1 as output, there won't be a 1 here, right? That is a very pretty simple logic. This is a equivalent diagram to n bit inputs, but there will be only one output, right? 1 bit output. It's either a 1 or a 0. The other method for finding equality is we can subtract it. We will come to that later. So the second type of a comparator is a magnitude comparator. So in magnitude comparator, we don't want to not just know whether the two numbers are equal or not. We want to know which one is the larger one. So in this case, consider this equation for the case of A is less than B. Right. So what is the condition of A is less than B? Either MSB of A is 0 and MSB of B is 1, right? That is, A starts with 0, it will be 0 something, and B starts with 1 and it will be 1 something. If that is not the case, if A and B are the same, then that is if A XNOR, this is the first condition, that A is 0 and that is A n minus 1 is 0 and B n minus 1 is 1. If that is not the condition, then what is the other condition? Both MSBs are same, and at the same time the next number, the next bit, that is the bit next to the MSB, for that the earlier condition, what? The A n minus 2 should be 0 and B n minus 2 should be 1. If that is, it will be either 0, A will be 0 0 something and B will be 0 1 something, or A will be 1 0 something and B will be 1 1 something. If that is not the case, then we just extend this logic, that is MSBs are equal, then digit or bit next to the MSBs are equal, then the third one we will look at, that is A n minus 3 is 0 and B n minus 3 is 1, that is 0 0 0, A will be 0 0 0 something and B will be 0 0 1 something, or A will be 1 1 0 something and B will be 1 1 1 something, like that. This we just extend the logic till the last bit, till the LSB, right? If this equation equals to 1, then A is less than B. For this, only one has to hold, right? Only one of these terms has to hold. Only one of these terms has to be true for the whole expression to be true, because we are combining them using or logic. So if the first case is true, then that's it. We don't have to look further. But if it is not true, then we have to look one by one. That is the logic we are using here. So A greater than B, we just switch the roles of this one, what? A and B for this condition. So let's see a simple 4-bit implementation of this logic. So here to find whether the bits are equal or the numbers are equal, we are using this XNOR logic combined with an AND logic, that is A equal to B. Okay. Then we are simply using what? This equation, right? Which is this one. That is the first condition is A3 bar and B3, that is given to the OR. So this will be A3 bar and B3 OR. What is that? What is the next term? What is the next term? The MSB is equal, but the next term is not equal, right? So it will be A3 XNOR B3, the equality condition, but the term next, that is the next bits are not equal. So this will be A3 XNOR B3 and A2 bar and B2. So up to here, what is the equation? A3 bar and B3, or A3 XNOR B3 and A2 bar and B2, right? Similarly, we extend this for all 4 bits. This is an OR gate. So now we have A less than B. We have the logic for A equal to B and we have the logic for A less than B. So how do we find A greater than B? We don't have to implement this whole logic for a next stage. What we can do is simply NOR them, right? So if for 2 given numbers, if it is not equal and if A is not less than B, then obviously it will be A equal to B. So if to find the condition whether both of these are 0, we use a NOR gate, and that will be A greater than B. So this is the magnitude comparator. So in magnitude comparator is a complete comparator in which we will get the 3 conditions: A equal to B, A less than B, and B greater than B. Okay, but the problem here is that as the number of bits grow, the number of gates required will be higher. For example, here we are using an AND gate. We are using a 4-input AND gate. Here we are using a 4-input OR gate. So as we increase the number of bits, it will be difficult to implement this actually, right? Because of the fan in and fan out problems of gates. So in reality, how we implement when we come to the paradigm of a computer architecture, how we implement a comparator is simply by using a subtractor. Right. So a minus b. For a minus b, if the MSB, and if you remember 2's complement notation, MSB usually MSB will be giving the sign of the number, right? So this is the difference. Here we are getting the difference. So if the MSB, that is, if we consider this as y of yn minus 1, if it is 1, remember, if it is 1, then what is it? What is the meaning? It means a is less than b, right? It means this is a negative number, and if the difference of two numbers is a negative number, then it means the first number is less than the second number. That is what we are taking here. We are adding this number with this bit with 1. So that is, only we will get a 1 here only if this is also a 1. So we get a less than b. Here we are using the same logic. If a is greater than b, the difference will be a positive number and the ms will be a 0. So here the 0 is inverted, it will become 1. So it will be a greater than or equal to b. We cannot say if all this is the same or not, right? So we get a less than b and we get a greater than or equal to b. So we will stop there for this lecture, and the next one we will continue with other digital electronics elements which are required for computer architecture. Thank you.